Okay everyone, this is a video on the first physics paper. Okay, the exam board is OCR, it's physics, and it's the first paper you're going to sit, which is also the paper you sit at the end of year 10 for your mock. So these topics are relevant for foundation and higher. Triple tier students will need to do some additional topics as well, and I'll cover those in a different video. Okay, so your first topic that you studied was in year 9 on matter, which is all about the particle model. Fundamental particle really has to be the atom. It is the smallest unit of an element that has the properties of that element, and you need to know the structure well, which you should know by now because you've clearly revised that for your chemistry exam. Right? So you've got a nucleus with neutrons and protons in it, surrounded by electrons at different energy levels. Okay, something you need to be aware of is how our understanding of the atom, our model of the atom, has developed over time. Well, we started off with Dalton's idea that we've got these little spheres. Okay, Chadwick discovered the neutron. Thomson is a key one that they want you to know about, the plum pudding model. Plum pudding, what's that? Think of a Christmas pudding. Okay, if you're not sure what that is, think of a blueberry muffin. Okay, the electrons are embedded in a positively charged mass. The electrons are a little bit like currants in a Christmas pudding, or if you like blueberries in the blueberry muffin. If you prefer chocolate chips, that's fine, whatever. It's just an idea. Okay, we've got a positively charged mass. Okay, and then we've got these electrons in there. Okay, and we've got this idea that there's charge in an atom. Overall, the charge needs to be neutral. So however much positivity we've got, we're going to have the same amount of negative to balance that out, because overall an atom has neutral charge. Rutherford did an important experiment using some gold foil. He fired positive alpha particles at an atom and discovered that actually most of the time they just went straight through, but they were also sometimes deflected. Now, the conclusion from that was that all the mass of an atom, pretty much nearly all of it, is in the nucleus. Okay, protons and neutrons have a relative mass of 1 each, and that explained why some of the alpha particles were deflected, because like charges repel, and he was firing these positive particles that were repelled sometimes when they got close to the positively charged nucleus. So Rutherford is the one that's responsible for redrawing this model that Thomson came up with, okay, with a positively charged nucleus surrounded by electrons that must be around the outside somehow. It's kind of orbiting. Bohr later on refined that by organizing those electrons in shells, depending on how much energy they have. Okay, but the overriding idea that you need to be aware of is that our understanding of the atom has changed over time because of new evidence. Okay, the second part of matter is using this particle model, the idea that matter exists as a solid, liquid, and a gas. You need to be able to reproduce these very carefully. Okay, in a solid, the particles are arranged in a regular fashion. All the particles are in contact with one another. You cannot compress a solid because they're already squashed together, essentially. Okay, a liquid, this diagram isn't particularly good. A liquid can't be compressed either because these particles should already be touching one another. The difference between a liquid and a solid is the fact that they're now in a random arrangement. Okay, so solid is a regular arrangement but touching. Liquid is a random arrangement but touching. You cannot compress a liquid. Gas is a random arrangement that are not touching. They are spaced apart. There is nothing between gas particles. Okay, there's nothing here. Nothing. Okay, certainly not air. These particles might represent the air particles, for example, maybe oxygen. Okay, there's nothing in between those. Okay, the idea that we can change from a solid to a liquid to a gas, you need to know the names of those processes. From a solid to a liquid, think about a block of ice out of your freezer at home. Okay, we go from ice, which is solid water, to liquid water, to gaseous water. We might call it the steam if you boil the water in a kettle. Okay, it's all water. Okay, but we can have solid water, liquid water, or gaseous water. All right, we can then cool that back down again. We can go from gas to a liquid. We can condense it. We can go from liquid to solid. We can freeze it. Okay, know your state changes. Okay, in both directions. Think about the particles. You should be able to describe the arrangement of particles. Okay, regular for solid, random arrangement for liquid. Gas particles are randomly arranged. They have random speed and direction. Okay, you can describe those state changes, which are a physical change, by the way, because it's reversible. Okay, you might get a graph that looks like this. If we've got temperature up on the y-axis, it's not very clear, sorry, on the screen. We've got time on the x-axis. The important thing here is that when there is a state change, okay, for example, here we're going from a solid to a liquid. Whilst the state is changing, the temperature does not increase anymore because the energy that is being transferred to those particles, imagine we're heating this up, no longer is the temperature rising because that energy is being used to overcome the forces that are holding those particles together. Once it has finished changing state, then we can start increasing the temperature again. Okay, so we get to 100 degrees Celsius if this is water. The temperature is specific to the element we're talking about. Water, pure water, has a boiling point of 100 degrees Celsius. Once again, we've got a state change. We're going from a liquid to a gas. Okay, liquid water to steam. The temperature stops increasing whilst that state change is going on. You can identify the state change by this horizontal part of the graph. Know that that is what that is showing. If we've got temperature on this axis and time on this axis, we're talking about state changes. Okay, whilst the water is heating up and there's a temperature change, okay, you can talk about this particular equation, mc delta theta. Okay, know your letters. Okay, C is for specific heat capacity, M is mass. Delta theta is the symbol that's used for a change in temperature. Make sure you recognize that and know what it means. Okay, capital E is with the energy that's transferred. Okay, so if there's a temperature change, we're talking about the sloping part. Where there isn't a temperature change, we're going to have to use an equation that has not got delta theta in. And there is one, it's E equals mL. That's the capital L there is for the latent heat of vaporization. Okay, so be aware that there are two equations that can be used with this graph, depending on whereabouts on the graph we are. Now, if you get a question on pressure, basically pressure is all about the collision of particles against the side of a container. Okay, collisions is a key word. That's how we can explain how pressure might increase. If we increase the temperature, there are going to be more collisions because those particles are traveling more quickly. They're going to hit the sides more frequently. They're going to be transferring more. They're going to be applying more force if they're moving more quickly because they're going to be hitting the surface harder, if you like. Okay, so think about pressure in terms of number of collisions per second of the particles against the side of a container. Okay, but you do need to know a little bit about pressure. Okay, you might remember that pressure is equal to force divided by area. Okay, so to have a large pressure, we have to have a large force over a small area. Also in year 9, you talked about motion. Okay, we introduced the idea of motion of an object. Okay, you need to know that speed equals distance divided by time. You need to know that speed is a scalar because it just has a magnitude of size only. Velocity is a vector because it has size and direction. Okay, be really careful. Okay, what have we got on that y-axis? Okay, because there's a big difference between the distance time graph and one of these, which is very different. It's velocity time graph. Okay, and we get different information from each. Right, so let's look at a distance time graph first. You need to know for sure, okay, that if it's a distance time graph, okay, we're talking about speed because speed is distance divided by time, and that is the same thing as the gradient of a graph, okay, because the gradient is the y-axis divided by the x-axis, or the change in y divided by the change in x, if you like. Okay, so from your maths you might remember this: change in y divided by change in x gives you gradient, which in maths is given as an m. So if we've got a distance time graph, a steep line represents a faster object. A less steep line represents a less fast object. So this cat is faster than the dog. Okay, that makes sense. For the same, after the same amount of time, let's look at 40 seconds. Who has travelled the furthest in 40 seconds? The fastest object has travelled furthest in 40 seconds. So it's the cat. Okay, the cat has travelled, okay, 32.5 meters. Okay, whereas the dog has only travelled about 25 meters. Okay, it's a good idea in an exam to actually do this, show that you've used a graph, do it better than I've just done, use a ruler, do it accurately. Okay, you will often have to extrapolate or get information from a graph. Show that you've done it, show the examiner that you've done that by drawing on the graph, but you do it in pencil and you do it with a ruler in case you make a mistake. All right. On a distance time graph, you will often get something like this, which represents maybe a journey. Okay, this is one of the rare occasions when sometimes you might join the dots up. Okay, we often say in science, do not join up the data plots. Within a distance time graph, you do sometimes get it like this, though, where it's not a smooth line of best fit. Okay, it's a little bit of an exception to the rule. Okay, but a change in distance over time, that's a speed. It's a nice straight line, so we've got a constant speed as opposed to a changing speed, which would be a changing gradient. Okay, so a changing speed might look like that. Okay, so if an object is accelerating, its speed is going to be changing, the graph will be getting steeper and steeper and steeper. Okay, so a straight line is a constant speed. Okay, here we've got a horizontal line. So I've got a horizontal line here. Okay, the distance is neither going up nor down. Okay, the distance is remaining constant. A horizontal line means we've got a constant distance. Okay, think about it. If the distance is not changing, it must be stationary. But please be careful, okay, because you might have a velocity time graph. Okay, now a velocity time graph is very different. It's a bit more complicated. There's more information we can get from a velocity time graph. So you really need to read those axes carefully. Okay, on a velocity time graph, if I've got a horizontal line, it means that my velocity is not changing. It's not, the velocity is neither going up or down. I've got a velocity though, it does not mean stationary. Okay, here I've got constant velocity. Okay, now my gradient represents a changing velocity, a change in velocity per time. What is that? Now we're talking about acceleration. Okay, this is why it's so important to label your axes on a graph. It makes a huge difference. Okay, suddenly the gradient means a different thing to what we had a minute ago when we were talking about a distance time graph. Okay, so velocity time graph, we've got a constant velocity. Gradient represents a change in velocity, i.e. we've got acceleration. Okay, and also we can work out a distance from a velocity time graph because distance is given by the area beneath the graph. So if I want to know how far I've travelled between 1.8 seconds and 6.4 seconds, I can calculate the area of that triangle. Okay, if I want to know the total distance travelled over the whole graph, I can calculate the area of that rectangle and I can add it to the area of the triangle. So we need to know that for a distance time graph, okay, the area equals the distance.